the dipoles are equal and opposite. Here, the dipoles are not equal and opposite. One dipole moment is going in the upward direction, and three dipole moments are going in the opposite direction. So 1
Yeah.
versus 3. So it is not 0, right? So this is written in like language that you need to write in your exam. So concept is clear, I hope, how this is working. Do you have any doubts with the dipole moment?
Why do we represent the arrows with a plus sign kind like
It
this
is not
across in the?
like
What does
this.
that mean? Yeah.
See, this means that we are showing the density, like electron density from left to right. This tail thing is showing that this area where the tail is represented is having low electron density. But
Okay, okay, okay.
if you see it with the arrow part, then you can say it has higher electron density due to what?
Yeah, understood.
What is the reason behind the dipole moment? Can you tell me? What is the main reason because of like why the electron cloud is shifting at the first place? What was the reason?
Mm, uh, it's because
Mhm.
it needs to like it requires uh, the basically I'm saying it negativity.
Your voice was not clear. Can you please repeat what you said?
Yeah, electronegativity.
Good, good. That's the correct answer. Electronegativity is the reason behind the shifting of electron
Yeah,
cloud. Good. So now let us talk about few application of dipole moment, right?
mm,
In determining the polarity of a bond, you can easily understand if dipole moment is more, then the bond is more polar, the molecule is polar, right? Because polarity is induced because of electronegativity and which result into dipole moment. So if dipole moment is more, this is the value of dipole moment. That
mm,
D is the SI unit, which signifies debye, right? So if the debye is more, then you can say the molecule is more polar. So with the help of dipole moment, we can comment on the polarity of a molecule, right? What else in the calculation of percentage of ionic character, right? I will tell you, this is our Fezan rule, Fezan set. I will explain like just give me a few seconds. Let us complete this one first. And the last application is in determining the symmetry of the molecule, right? So if
yeah.
the dipole moment is there, then it is also going to affect the symmetry of the molecule because you can understand or imagine it like if your dipole moment is more, the electron cloud is more shifted. So it would directly affect the the geometry of the molecule or not, symmetry, right?
Mm,
So let us talk about what do we mean by calculation of percentage of ionic character, right? So there was a
yeah.
scientist, Fezan, what he said, uh, partial covalent character of ionic bond. So basically what he said was, whenever you are like forcing two ions, a cation and an anion towards each other, right? A cation being a positively charged species and an anion being a negatively charged species, the moment you have put them into their like electric field region, they will automatically start attracting each other or not because they have opposite signs, right? So once my cation is reaching my anion due to the attractive forces, they will come close to each other. What Fezan said, if my cation is small, very small, and corresponding
Mm-hmm.
anion is very large, if my cation is very small and my corresponding
And my
anion is
anion is
very large,
large.
then we will observe a better bonding. This ionic bond will lead to covalent character. This so-called this like you can see there are ions which are involved. These ions which are involved here will lead to covalent character. So if you read it with me, what is written over here is when a cation approaches an anion, the electron cloud of anion is attracted toward the cation and gets distorted. The effect is called polarization effect, and the power of cation to polarize the ion is called polarizing power. Okay.
Okay.
So the smaller the cation and bigger the anion, more what you can say, more polarization will occur.
Um, what is polarization effect? Like, what does it mean?
See, if you see it over here, this is your
Like,
cation.
is it like a better bondage?
Uh, it will be a better bond. See, this is your anion, for example. When they are reaching each other, it is a cloud, right? It is a cloud.
Uh-huh.
When a cation is reaching it, it will distort the anionic cloud. This cloud, which was supposedly be like a sphere, it will convert into something like this. It will be distorted due to the cation. And due to this distortion, what we will observe is beta bonding. So this is what polarization effect is. The distortion of anion due to the cation is polarization effect. Distortion. Are you getting what I'm trying to say? Shape is getting
Distortion
distorted.
of cation
Anion.
due to anion.
No, opposite. Distortion of anion. Anion is big.
Yeah,
Anion
yeah,
is
yeah,
very
yeah.
big. So it is easier to distort it.
Due to cation. Okay, okay.
Yeah, this is your polarization. So let us see factors on which polarization depends. Small size of cation, as I mentioned, and large size of anion. If your cation is small and anion is large, there will be more polarization. We can see it with this example here. Lithium is small cation and
Mm-hmm.
iodine is the biggest halogen. If you compare fluorine, bromine, and iodine, the sizes are as follows, right? The
What
biggest
does
halogen being
halogen mean?
halogen is the name of these compounds. The group 17 elements
I know
are
that, but what does it mean?
basically
Like
halogens
the
are
what characteristics does it have?
electronegative nature. All of these elements have 7 electron in their outermost shell, right?
Yeah,
All of these elements have 7 electrons in their outermost shell. So they have
yeah.
higher tendency to gain an electron rather than losing it.
Oh,
Because if they gain 1 electron only, they will possess a noble gas configuration, right? So they prefer to gain electron rather than losing. So if something is like something has a tendency to gain electron, then what we call them? Electronegative
halogen.
because
Or
halogens, right? Electronegative element.
okay, okay.
So
So
here this
chlorine is a halogen then.
chlorine, fluorine, bromine, iodine, all of these are halogens. All group 17 elements are halogens.
Okay, now I understood. Okay.
So here my cation is same, right? This cation is same. Lithium is our cation and it is same for all the compounds.
Yeah.
But what we are changing? Here we have fluorine, then bromine and iodine. As I am moving from
Uh,
fluorine to iodine, what I am observing? Increase in size of an ion. And what we just studied, if my anion is large and cation is small, then there will be more polarization. This was all about our Fazan's rule, or not? So if you're like,
so so anion size will be largest in lithium iodide
lithium is same. It is a small cation and it is same for
in
all.
iodine then.
See, let me draw it here. Suppose this is your lithium. This is your lithium. This is your lithium. Lithium has same size. What we are basically changing, we are changing our anion.
So now I know that what I've learned that um if the okay the larger the anion or like orbit is of an atom,
Mhm.
um the less the tendency will be to gain the electron. Like fluorine is more electronegative, like the most electronegative, right?
Yes, yes.
um but it is the smallest radius amongst the halogens.
Okay,
um
okay.
so but iodine is the least, but it has the largest radius amongst the
Mhm.
halogens. So I have
Okay.
learned that it's in like indirectly proportional to the electro negativity.
See, the thing is, you are somewhat right. The thing is, I think you are saying that iodine will have most electronegativity. Like, are you saying something like this?
No, iodine has the least because it has the largest radius.
Yes, because F is small, right? You are saying something like
Yeah.
this is correct. But you have to here you have to understand in terms of Poisson's rule. Your concept is clear. The thing that
No,
you are
I'm
saying is
just
correct.
saying what I
It is correct. It is
personally
correct.
know.
It is correct.
Is it correct? Yeah. I'm not saying in this topic. I'm just personally
Overall, right?
saying.
No
Yeah,
issue, no issue.
overall. Yeah.
So the thing is, are you like, is it clear what is Poisson's rule?
Yeah.
Right. So in your exam, they might ask you this question like, in out of these compounds or molecules, which
Mhm.
one has most polarization? So you will see the smallest cation as the cation is same. So what else you can look for? The anion size. If the anion is biggest, the polarization will be the most. And you know the size of iodine is biggest if you compare them with their like
Yeah.
relative halogens. What else? What else? Charge on atom. If charge on atom is more, then more will be the polarization. That is all about Poisson's rule. From your exam point of view, they won't be asking any much. Like if you read this, it is sufficient, right?
Yep.
Okay, so let us move ahead. These are some questions about dipole moment, and these are very important. So you should know why in carbon dioxide the dipole moment is zero. Can you answer this? Why? Out of carbon and oxygen, which atom is more electronegative?
More electronegative.
Yeah. And one more
It
thing
should be
hmm,
oxygen.
good. Do you remember I told you something? It is not necessary that if two atoms have different electronegativity, the molecule is going to be polar. We have a certain value. The difference should be bigger than that. What was that value?
Electronegativity value.
Electronegativity difference value.
Yeah. It's
What
a
was?
dipole.
No, no, no. See, I told you in the last class, if
It's
we are
like
talking,
mu.
this is I, you are, like, see, if we are talking about this molecule, right?
Mm-hmm.
They have difference in electronegativity or not?
Yeah.
They have. If I am talking about HF, again, difference in electronegativity, but are we going to say these both molecules or bond have polar character? No. Only those bonds will have polar character where the electronegativity difference is more than 0.5. What is the value for fluorine, the electronegative value? It is 4, I guess. 4 or 3.5.
Yeah.
I'm not sure. Can you check
Fluorine,
on
right? Fluorine or which one?
fluorine, fluorine.
Yeah, four only.
Okay, what
No,
about
no,
carbon?
fluorine is 4.5.
It is 4.
It's
Okay,
four?
yeah. What about carbon?
Uh, Carbon, it should be 2 point something.
Let us Google it. What is the electronegative value for carbon?
2.5.
2.5. Okay. So the difference here is 0.3.
Yeah.
Only those bonds will be polar where the difference in electronegativity is more than 0.5, right?
Yeah.
So this bond is not polar, although they consist different electronegative elements. Is this clear? Only those
Yeah.
elements where the electronegativity difference is more than 0.5, only those
Yeah.
molecules we will call them polar. So back to our question, why CO2 is non-polar? Why the dipole moment is zero? Tell me.
Yeah, just a minute.
Mm. You have to consider dipole as a vector quantity.
Yeah. Um, okay, just a minute.
Mm. Take your time.
So I didn't understand the question. What is the question, by the way?
Why CO2 molecule has zero dipole moment, although the molecule consists atoms with different electronegativity, and the atoms are fulfilling the criteria where we have to see whether the difference is more than zero point 0.5 or not. After all this,
Okay,
why this molecule as a whole is still non-polar with
okay.
dipole moment?
Why the CO2 is difference? I mean, dipole moment of CO2 is zero,
Mhm. This is your
and
question.
H2O is not
Yes.
correct. So because the difference is the difference of the what do you say? The difference of the electronegativity of one carbon and two oxygens. Should we account two oxygens or only one oxygen for the
You
electronegativity? Huh?
see, if you are talking in terms of molecule, then you have to consider all that.
So we need to include one more also, right? So the
Mm.
difference is less than zero point 0.5. So so it's close to zero. So
It is
the
exactly zero. It is exactly zero.
it is exactly zero.
See, think
Hmm.
about it. Now, I told you, see, if my dipole moment, see, if you see this specific bond, right? It is
Hmm.
showing that the electron density is moving from left to right, from carbon to oxygen. And on the other hand, we are seeing the
Oh, okay,
same
okay,
thing,
okay.
the carbon from right to left, and they are pulling the electrons with same strength. If I am pulling
Yeah,
the rope, if I am pulling the rope from this end and other person who have same strength, if you compare him with me, he is pulling the rope from the right, like opposite end. Then
yeah, I
is the
understood.
rope going to is the rope going to move anywhere?
I
No.
have studied this. Yes, yes, yes.
So that's the reason. Due to equal
Yeah,
and opposite dipole,
it's going opposite directions. But
equal and opposite,
H2O is going in one direction. That's why.
it is adding up from hydrogen to
Yeah, it's
oxygen, then
adding up.
oxygen to lone pair. This is
Lone
the
pair.
reason. Right?
Okay.
Is this clear?
Yeah.
Okay. These are some significance like applications that we already discussed, right? What is electronegativity? How does it differ from electron gain enthalpy? I told you this like in the third chapter as well. So you can go through the answer. I think you will be easily able to understand because we have talked about this several times. Can you
Yeah.
tell me, like, without looking at the answer, what is the difference between electron gain enthalpy and electronegativity?
Electron gain enthalpy and electron. Okay.
Hmm.
Electron. Um.
We might be able to complete this chapter today. Let's go.
Yeah. What is electron gain enthalpy again?
See, the name itself defines what electron gain enthalpy is. Try to
So
think about it.
gaining the electron.
Yeah, where we are basically the like electron exchange is happening in which shell?
Um. Gains in the valence shell.
Valence shell. So what is electron gain enthalpy? Electron gain enthalpy is the tendency of an atom to
Okay,
gain an
okay.
electron
So
in its outer motion.
enthalpy means the tendency, right?
No, enthalpy is simply energy. Electron gain
Okay.
enthalpy.
So electron gain enthalpy. Okay. Yeah, this is easy.
Hmm.
So the electron gain enthalpy is about energy that is required to gain or gain electron. But what is the other one? Which one you need
Negativity. Electron
negativity?
negativity.
Yeah. Electron negativity is that it is the tendency to gain the electron of an
No.
element.
See, see. Try to like you can note it somewhere because it is important. Electron gain enthalpy is the tendency of gaining an electron, or you can say the energy released when you are adding an electron to an outermost shell. But what is electronegativity? Electronegativity is after the bond is formed. Once the bond is formed in this molecule, in this bonded molecule, uh, in this bonded molecule, the tendency of electron cloud to be shifted. Like chlorine is more electronegative, so it will pull the electron density from on itself, basically. So in bonded state, electronegativity works. But if it is not bonded state, you will call it electron gain enthalpy if you are adding the electron. Electronegativity is a phenomena which we talk about when we are talking about a molecule in a bonded state, right?
Yeah.
Is it clear? So these are some other questions purely based on the topics that we have discussed. And this last one, you need to be like, you need to give it some importance. They might ask you directly this question. All of these questions are from your NCRT, and this one is a bit important because they have asked this question several times. So you should know what they are asking. Ionic character. I told you the smaller the anion, sorry, the smaller the cation and bigger the anion, more will be the polarization. Polarization is more, than ionic character will be more. What else? Positive or negative charges, right? So this is
Yeah.
all about it. So I would request you to do it yourself. Think about it. The points
Okay.
that we have discussed, cation should be small, anion should be large, and charges. If charge is more, suppose if we have plus one charge or plus two charge, the plus two charge cation will cause more polarization. So try to give it some thoughts. You will be able to understand it if you just think about it. Now, the last topic of our chapter is molecular orbital theory. It is, I would say, like one of the most important topics from this chapter because in your exam they are for sure going to ask you question from this topic. So let us try to understand it. What is molecular orbital theory? So far what we have discussed, we started with Lewis dot structure. Then we talked about VSEPR theory because Lewis had some drawbacks and our VSEPR theory somehow fulfilled some of those points. But VSEPR theory still had some its own drawbacks. So to
Yeah.
complete or like answer the questions in VSEPR theory, who came? VBT, valence bond theory. In valence bond theory, what we understood? In valence bond theory, we understood like whenever two atoms are approaching each other, there will be several forces, new interactive forces that will develop, and if the attractive forces are dominating over repulsive forces, then the bond will be formed. Otherwise, it will not form. Right.
Yeah.
So after that theory, we have another theory which is molecular orbital theory. It is more defined. Both of PBT and molecular bond theory are based on quantum mechanics, but this is a more like this theory was discovered on a later stages, like after I guess 20 or 30 years later. So this is the, you can say, later version of PBT. So
Yeah.
molecular orbital theory, let us talk about it. This theory is based on Lacau, linear combination of atomic orbitals. So one thing is clear. In a molecule, we have atoms, right? So when we are talking about molecular orbital theory, then we can say for sure some atomic orbitals are combining. Okay. In molecular orbital theory, we can say some atomic orbitals are combining. Now we have to talk about how the molecules are combining. This is your whole molecular orbital theory basically. So let us see. When two atomic orbitals undergo mixing according to Lacau principle, they will form two molecular orbitals, BMO and ABMO, bonding molecular orbital and anti-bonding molecular orbital. So we talked about a similar thing where we were merging orbitals. Like in hybridization, what we were doing, we were again merging two orbitals, right?
Yeah.
In hybridization, what was happening? We were merging two orbitals to get a hybrid orbital, which is having equivalent energy. So how
Yeah.
our hybridization is different from molecular orbital theory? So let us talk about it. So in hybridization, what we were doing? In hybridization, we had different atomic orbital, right? If you talk about 2s, it is a different atomic orbital. If you talk about 2p, it is different. They both have different energy as well. The purpose of hybridization was to get a orbital, set of orbital, hybrid orbitals which have equivalent energy. Can you answer me why this is important? Why we need this hybridization? Why we need orbitals to have same energy? I told you this in the last class. What was the reason?
Yeah.
Hmm.
To like for reactions, because they won't react if they're like not in their hybrid form.
See, let me give you a hint.
Stabilization.
No, no, no. Let me give you a hint. Suppose you have four friends, right? And you both have to purchase something, right?
Yeah.
You and your three other friends are going to a market, and you both, all of you have to purchase a thing. And you went to a shop. There are four pieces, four things that you need to purchase. But all
Yeah.
of them have different, like you can see them. This one looks better. The other one is a slight, not like it is not that better than the first one. As you are moving from left to right, you are observing a trend. Like the first one is the newest one, and the last one is the oldest one. So which like, let us talk about what do you want to purchase these days? Any game?
Mm, I guess like I don't know. I
Tell
have
me
no
anything.
prefer. Okay, let's just say games then.
So, any specific game? GTA.
Um,
Played
yeah,
GTA?
yeah, yeah, yeah.
So let us
I
see.
heard of it.
See. Uh, on the left hand side, you have GTA 6. On the As you're
Mm-hmm.
moving from left to right, it is GTA 5, then GTA 4, GTA 3. All of them
Mm.
have same price. So which one would you prefer?
GT6 because it's the
GTA
latest
6,
one, no?
latest version. So you have four friends, and all of them will fight for that one because the price is
Yeah,
same. So they will say like, I need to purchase that as well. So this will create what? Instability. This will create repulsion between the friends, or not? So what
yeah,
our central atom do to avoid this fight? It produces orbitals of same energy so that your electron won't have a choice. The electron won't fight for the orbitals, right? So this is the whole reason.
yeah,
So suppose if electron was here, out of P or S, in which orbital would electron want to go? The one with lesser energy. So all the electrons would want to go to S orbital. But
uh-huh,
in one orbital, we cannot fit more than two electrons, so it will create instability. So what our central atom do, it will create hybrid orbitals. In hybrid orbitals, all the boxes are same energy, so that your electrons won't fight or create instability. You can understand it like in your table now, you have all GTA 6. So all of your friends can purchase it without having any fight, right?
why is there a four oh, okay, 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 okay. Yeah,
Because you are four friends.
yeah, yeah, I understood, I understood.
If there was three
So
friends,
only
then
one person is getting GTA 6 and one person is I mean three of them is getting five.
no, if the orbital is hybrid, all of you are getting GTA 6 because they are same. All of these four
Okay.
orbitals are same, but here
Oh
they were
yeah.
different. Here
Okay.
it was GTA 5, it was GTA 6. You all were fighting for this, and they were GTA
Uh-huh.
5, GTA 4, or GTA. So what shopkeeper did? He replaced all of them and just placed all GTA 6s
Okay, okay, okay.
to avoid fight. Right?
Yeah, I understood.
So what about molecular orbital theory? How it is different from hybridization? So in hybridization, we were merging two different atomic orbitals with different energy. But in molecular orbital theory, we are not using orbitals of different energy. We are using atomic orbitals of same energy. How it is different from hybridization? In hybridization, we had different energy orbitals. But in molecular orbital theory, the atomic orbitals have same energy. But once they are combining, they will produce molecular orbital with different energy, right? Atomic orbital of same energy merging to give molecular orbital of different energy. This is molecular orbital theory. The atomic orbitals in higher energy states are called anti-bonding molecular orbitals. The energy
Yeah.
orbital in lower energy state are called bonding molecular orbital. Is this clear? This is your energy curve or energy axis. As we are moving from top to like bottom to top, the energy is increasing. Is
Yeah.
it clear? Do you have any doubts on
Yeah.
this?
So the bottom one gets filled.
Huh. The one with lower energy will be filled first.
Then the higher energy.
Yeah. Okay.
Okay.
So this is your question in NCRT, question number 34. Mixing condition. What are the mixing condition? If you are mixing two atomic orbitals, how you can make sure the mixing is better? So the conditions are, for better mixing between atomic orbital, the energy gap between two, what is this? The energy gap between atomic orbitals should be less. The energy gap between these two atomic orbitals should be less.
Okay.
Atomic orbitals should have identical symmetry. These are the two conditions with the help of which you can produce better mixing, right?
Yeah.
And what else? This third point I have mentioned here as well. The combining atomic orbitals should have comparable energies. These two atomic orbitals should have comparable energies, and the energy gap between atomic orbitals. This energy gap should be less, and atomic orbitals should have identical symmetry. These are three reasons. Is this clear? If you have any doubt till here, please ask, because we are going to develop the concept on the basis of these few topics.
Um.
Hmm,
Hmm. Well, just a minute. Just be in this page for a minute.
hmm.
Can you go down? Yeah. What does condition mean? Mixing of orbitals?
See, whenever you are mixing two atomic orbitals, there would be some
Hmm.
specific condition with the help of which you can mix the two atomic orbital with more ease, right? So these are the
Okay,
conditions
this
where the atomic
conditions.
orbital.
I guess, yeah, I understood.
Okay, so let us move ahead. See, let us take some examples as well. Okay. One s atomic orbital of one atom can combine with one s atomic orbital of another atom, right? So the last, uh, this this last point is explained by this example. If you have atomic orbital, it will combine with another atom's 1s orbital with ease, and so the 2s1. Is this example clear, or should I expand it more?
Yeah, I understood that. But the second one?
The extent of overlapping should be large. This overlapping region should be big.
Yeah.
That's it.
Okay. Yeah, understood.
So in your syllabus, you are fortunate that you don't have to talk about molecular orbital theory for like molecules with much electronegativity difference. So you should be, you should feel like, I mean, relieved that you have to only talk about these type of molecules, and they are very easy. So let us see what we need to talk about. Hmm. So what do we mean by A2? A2 means that both the elements are same. If you are talking about hydrogen, then both of them are hydrogen like H2. If you are talking about oxygen, then both of them are oxygen like O2. Basically, the molecule as a whole is non-polar with dipole moment zero, no electronegativity difference, right? But if you are talking about AB, AB means that electronegativity is different for A and different for B because A and B are different elements, right? If I'm
Yeah.
talking about this specific case, the electronegativity difference is there, but it is not that much. So it will look like this. But what if the electronegative difference is so huge that when you are going for the like when you are trying to combine the atomic orbital, they are not even combining. So you don't have to talk about this. I'm just giving you a brief. What are the possibilities when you are combining two atoms in molecular orbital theory? Okay.
Can you go up? Can you
Up.
explain them once again? I don't understand.
See, what do we mean by A2? A2 means both the elements are same. For example, H2, O2, Cl2, right?
Okay.
And if the both the atoms are same, is there going to be electronegativity difference?
No,
So you can say
it's
this.
gonna be zero.
This chi is basically symbol for electronegativity, right? So
Okay.
electronegativity is same. But if the elements are different, there is like going to be a electronegativity difference. If your B here is a different element, for example, it is CO. So there is going to be electronegativity difference. This B is your oxygen, so the electronegativity of B is greater than A, we can say, right?
Yeah.
So when the atomic orbital of A is merging with the atomic orbital of B, due to the more electronegativity of B, it will be slightly shifted towards the bonding molecular orbital, right? So ideally, if the elements are same, the atomic orbitals have same level. But as the the electronegativity of B is slightly higher, it will shift more towards the bonding molecular orbital, and we will have a slightly tilted set of molecular orbital, right?
Oh, oh, okay, 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 okay.
Okay.
So
Uh,
there's a tilt.
yeah, because of the electronegativity, because of the different
Mm.
atoms.
Okay, okay. Yeah, understood.
Bonding molecular orbital, BMO has more character of B, more electronegative, ABMO has more character of X. What if the electronegative difference is so huge that
Yeah,
one
I already understood that part also.
hmm, so for
It
like
becomes a
two shifted, like they won't be able to
yeah.
make
It
a bond
becomes a parallelogram.
parallel type. Okay, so you
Yeah.
have to like for like the extreme in extreme case scenario, like when we will talk about like J level questions, we will talk about only this. In your board level, you have to talk about only this, right? So let us talk about both of them. So before going into our molecules and understanding how they are merging, we have to understand the basics. What types of bonding, what types of like basically terms that are going to be used for molecular orbital theory. So let us get familiarized with that first. Okay, formation of molecular orbital, pictorial representation of molecular orbital. So when we are going to say a bond is a sigma bond, when the overlapping is head to head or not. Whenever the
Yeah.
overlapping is head-to-head overlapping, we will say the bond is sigma bond. So which sort of sigma bonds you are going to observe? It is going to be either one sigma 1s. What do we mean by sigma 1s? That means 1s orbitals are merging with each other. Okay,
Okay.
two different atoms 1s orbitals are getting merged with each other, and the bond arising from it is sigma 1s. Right? What do we
Yeah.
mean by star? This star means again, the merging is between s orbital, one s orbital, but the electron that are filled is in anti-bonding molecular orbital. Whenever you are showing electrons here, then you will show this star sign. This star sign indicates the electrons are residing in anti-bonding molecular orbital,
Why is
right?
it called anti?
Because it is in higher energy. Any electron which is here in this anti-bonding molecular orbital will not feel easy. It will feel instability because it is in higher energy. If you have to relate it in general terms, then you can relate it like this room at the this room at the bottom floor, like the ground floor, will have slightly cooler conditions, right?
Yeah.
The basement has slightly less temperature, and it will be like you can be there. If you are in a very hot area, the top floor is going to be very like hot, basically high temperature.
Hot. Oh,
So
okay, okay. Unstable area.
unstable. If you are living there, then you will feel like if you don't have access of AC, then you will be like cooked basically.
Yeah,
So the electron will feel the same instability. Okay.
yeah.
So the star is representing that the electrons, the bond which is formed is due to the antibonding molecular orbital. So on the basis of these 2 points, can you tell me what does it mean by 2s, sigma 2s?
Uh, Sigma 2s. Sigma bond is sigma bond with two s orbitals.
Good. And the electrons are residing in bonding molecular orbital. The box,
Regular.
the ground floor
It's
box.
in the down, yeah, low energy part.
So this is about your sigma bonds. These are the possibilities of sigma bonds here. And the last one is sigma 2pz and sigma
Yeah,
star 2pz. We will go into them in detail. And what other type of bonding we can observe? A pi bond, right? By
yeah.
sideways overlapping. So here, which type of pi bonds are you going to observe? It is sigma, sorry, pi 2px when the px orbital. See, these are our this is our s subshell. In this s subshell we have px, py, pz, and this p orbital looks like what? This y looks like this, and this z look like this. If we are talking about this px, then what do we mean? That two px orbitals are overlapping and forming a pi bond. Okay, is this clear?
Yeah.
And what do we mean by the that other thing? Star.
Star. Yeah, that's anti pi bond, which
Mhm.
means that it is in the top high energy orbital.
Yes. Okay.
Yeah,
So this is about our. So let us talk a bit more about this to understand it with more clarity, right? So head-to-head mixing. Suppose you are talking about sigma 1s. This is your 1s orbital, and the other one is 1s orbital. What is common here? They both have plus sign, right?
yeah.
If you are merging two atomic orbitals of like same, basically 1s 1s,
Why
and
is
the
it plus
sign
sign?
plus sign, I will tell you, like, just give me a few minutes. This plus sign is representing the area. Like electron has a wave nature, right? And if it has a
Yeah.
wave nature, it can exist in both quadrants. It could exist either in the plus quadrant or in the negative quadrant, right?
Okay.
When we are merging atomic orbital, when we are considering it, the electron is in plus quadrant. When like if we are merging it in that state, then the bonding which is arising is constructive bonding. Okay,
Okay.
they will merge. This is constructive interference, and because of this, the bond which is going to arise is sigma 1s. When you are merging two atomic orbitals and you are considering the positive phase, right? The bond which will
Yeah.
arise is the sigma 1s bond, the bond which is in lower energy. Okay, it is same for this one as well. If you have negative sign, if you are combining two atomic orbital with same sign, either positive or negative, the bond arising is constructive bond, which is going to lead for the formation of sigma 1s, the one with bonding molecular orbital, right? And it will have center of symmetry as well. Center of symmetry, what do we mean by center of symmetry? If I am walking from here to here, I am observing same environment, again same environment,
Yeah.
again same environment, same center of symmetry, right? Okay, note. Orbital has wave nature. Orbitals similar to our electron has wave nature. It possesses both positive and negative phase. One thing that you should note somewhere, this positive and negative sign is not representing the charges. Okay, because
Okay.
a normal
I was
person
thinking about that.
a normal person would think like why this positive and positive sign are merging with each other. They should repel, right? Why they are
Yeah.
merging? So because they are
And
not
first
positive
of all,
charges.
why is it a proton?
It
Like
is not a
why
proton.
proton?
It
I
is a
know it is
region.
not a proton.
It is not
It's
a
just a
proton.
region of electron.
Similar to electron, orbital has wave nature. And orbital also possess both, like positive region, it could exist
Does
in
the
positive
whole
coordinate.
atom have a wave nature?
Yeah, they have dual nature. We talked about this in the second chapter. At the
The
end,
whole atom.
huh, whole atom has a dual nature.
Okay. So that includes nucleus as wave nature.
See, basically, if you talk in terms of electron, and nucleus is not the smallest particle. See, you might have heard about the protino, neutrino, right? If you zoom into the
Yeah,
nucleus, you will find some other like subatomic particles even at the deeper level. And there are quarks, right? Have you heard about quarks?
yeah. It's
Uh,
the
so,
deepest.
so like we cannot uh scientist. I think I am not updated with this. The last thing I heard was quarks. Like the smallest thing that we have discovered is quarks, right? I
Yeah.
think they might be able to see into quarks as well, and they
No,
might find
there's only quarks. There's
till
nothing
now,
beyond
till now, no,
till
till
now.
now. So, as I mentioned in the first class, quantum mechanics is something that
That is scary.
it's pure chaos. Okay,
Yeah,
so what is when we are going to observe this star one? When you are merging two atomic orbitals with different signs. Okay, this we will call destructive interference, and after this, the bond that we are going to get is sigma star one is formed, and again it is going to be unstable. And here we are also going to observe a node. It is going to be an anti-bonding molecular orbital. Center of symmetry is going to be absent, and the other points we can say. Okay, sigma
yeah.
2s and sigma star 2s is same, nothing is changed, but the size of the orbital is going to be big. If you have represented the size of 1s like this, then you have to represent the size of 2s like this. Same. All right.
Yeah.
Now let us talk about this sigma 2pz. What do we mean by sigma 2pz? Sigma 2pz is different from sigma 1s or sigma 2s because here we are not introducing or we are not including the s orbital. We are talking in terms of p orbital, right? And p orbital
Yeah.
have different shape. But what was the common thing in sigma bond? The overlapping should be head to head, no matter whether it is sigma bond or it is a s orbital or a p orbital. So in
Yeah.
pz, what we are observing that these p orbitals are what you can say, they are suspended in the three dimension like this, and they are overlapping in head to head manner. Okay, so whatever bond we are observing by head to head overlapping is a sigma bond. So again here the signs are same and they are merging, and it is leading to a sigma bond which is sigma 2pz.
So
Again,
the pi bond is face to face,
mm, this is head to head. If somehow suppose
head to
it
head,
was uh,
but pi bond is face to face.
pi bond is face to sideways basically like this.
Yeah, that's what face to face is.
Okay, is this clear?
Yeah.
So you might come across a term internuclear axis. So I have mentioned what is internuclear axis. Sigma formed along that axis because axis is considered as internuclear axis. See, uh, if it is not mentioned, if it is not mentioned in your question, like about internuclear axis, you have always going to consider z axis as internuclear axis. If they have specified any axis as internuclear axis, you have to act with respect to it, right? So in most cases, your z axis is going to be internuclear axis.
Okay.
What about the star one? In star one, what is again different? In star one, we are merging the atomic orbitals with different signs. Whenever you
But
are merging
if
atomic orbitals in different signs, you are going to observe a destructive interference, right?
yeah.
Destructive mean unstable. Again, what is the significance in your? This is the question in your answer. Write the significance of plus and minus sign in representing the atomic orbital. Plus and minus sign is used to identify the nature of electrons wave. Plus sign denotes
Yeah.
rest, while negative signs denote denotes stuff, right?
Of
Okay, so let us talk about the pi bond. Uh, I hope it is making sense, right? In
Yeah,
pi, the sideways overlapping is there. And again, if the merging is between the same sign, then it will be constructive and leading to the bonding molecular orbital theory without the star sign. But if the same thing is happening between the opposite sign, like plus minus, then it will be destructive and you will
then it's
observe
a anti.
anti-good, right?
Yeah,
So this is the summarization here. You can go for it as well. Now, as we have gone through the basics, now let us see in terms of molecule system. Homonuclear diatomic molecular orbital diagram. What do we mean by homonuclear? Homonuclear means same atoms, right? Homo means same.
yeah.
So give me a second. Let me see how many pages are left. Mm, okay. See, there is one thing that you have to remember it. I will explain the reason as well, but it would be more better for you to just learn it. Okay.
Yeah. Can you give me a second? My friend is calling.
Yeah, sure.
Yeah.
Just give me some minutes. I'm just going to plug my
Yeah, sure,
charger.
sure, sure, sure.
Okay. So we are going to talk about the molecular orbital diagrams of few of these molecules, right? So we are going to talk about Li2, Be2, C2, N2, O2, and F2. Okay.
Yeah,
So the thing that you need to remember is the mixing. See, when we are going from lithium to nitrogen, we are observing mixing of S and P orbital. But as we have reached oxygen and we are going for fluorine, this sp mixing is stopped. Right? What it is going to like, what how it is going to affect our molecular orbital diagram. Let us talk about it. So generally, the energy levels are like this. The sigma 1s is having least energy, then sigma star 1s, then sigma 2s, then sigma 2s. Till here, it is same, right? Till here, it
yeah,
is same. In lithium to nitrogen, sp mixing is there. From oxygen and fluorine, sp mixing is absent. But till sigma 2s, the energy level, the level of energy is same. But as we are reaching from the uh, as we are moving from sigma 2s, sigma star 2s, then we are observing a change. Here we have sigma 2pz, right? But
yeah,
here we have pi 2px and pi 2py. So what is different here? These two atomic orbitals, these two molecular orbitals are going to get exchanged with each other because till here we have sp mixing, but after this we don't have sp mixing because of like no sp mixing in oxygen and fluorine. They will have this sort of atomic or molecular orbital energy profile, right? I will apply
Yeah.
this in the molecules. You will have a better idea. No sp mixing, total electron less than like total electron more than 14. sp mixing if the total electrons are less than 14. For example, this for lithium B2, C2, and 2, you have this sort of energy orbital, like molecular orbital energy level. For the elements which have electrons more than 14, you will follow this one. So let us see. This is your general molecular orbital diagram. Two atomic orbitals are merging and giving us bonding molecular orbital and anti-bonding molecular orbital, right? The
Yeah.
energy orbital is what? The highest energy has for anti-bonding molecular orbital, then atomic orbitals, then the least is bonding molecular orbital. This is your energy level. Okay.
Can you go up?
Hmm.
Uh,
Hmm.
okay. Why is it getting switched?
Because as you are moving from nitrogen to oxygen, the number of electrons are more than 14. And this causes the difference. See,
More than
14. Okay.
14, 1 4.
Yeah, 14. Okay. So what is happening is suppose till nitrogen, the S and p orbitals were near each other. They were not far apart. So due to which the sp mixing was present. They were able to exchange electrons. But as you are reaching oxygen, the s and p orbitals are now sufficiently far away from each other than that the exchange of electron is stopped. Because of this stopped electron exchange or stopped mixing of sp orbital, we are observing this exchange of molecular orbitals. Right? It will make
Yeah.
sense. Let us talk about some specific examples, then it will make much more sense.
Okay.
I hope till here it is clear, like the things that we have discussed previously.
Yeah, yeah, yeah.
So in your exam, they are going to ask you what is bond order. So for bond order, what you are going to do? You will have this formula half. This is number of electrons in bonding molecular orbital minus number of bonds in anti-molecular orbital. This is very simple formula. Okay. And this
Yeah.
is the relation bond order is directly proportional to bond strength, inversely proportional to bond length, and directly proportional to bond energy. This we have discussed in the third chapter as well as in this one as well in some parts, right?
Yeah.
So let us talk about the H2 molecule, the simplest one. If you have one H atom and another H atom, both have atomic orbitals. A atom is going to have atomic orbitals, right?
Yeah.
In hydrogen atom, we have one s atomic orbital with one electron only.
Okay, what does the side atom mean? I got the up one and downward. Up one is anti-bond, and downward is standard bond. What does the side one mean?
See, this is your bonding molecular orbital. This is your anti-bonding molecular
Bonding
orbital.
on molecular
These are
orbital.
your atomic orbitals. These are the reason these orbitals are getting existing. Like they are existing because of those atomic orbitals. They are the reason. They are merging with each other and creating molecular orbital. Two atomic orbitals are merging and creating molecular orbital.
Okay.
Right? These are your atoms orbital. See, this is your hydrogen atom. This is your hydrogen atom, right?
Yeah.
And it has its own atomic orbital. It has its own atomic orbital. They are
Okay.
coming close to each other and they are merging and giving us what? Molecular orbital. One is anti-bonding molecular orbital and another one is bonding molecular orbital. One hydrogen has one electron. Two hydrogens will have how many electrons?
One hydrogen has.
One electron and two will have two.
Yeah.
Now you have to fill these two electrons in the molecular orbital. So you will start from bonding molecular orbital because it has low energy. You will start like this. You will fill two electrons like here. Do you have any uh,
Oh,
left like do you have any electrons which are left? No. So this is your molecular
no.
orbital. So this is your what?
But what about the anti-bond molecular orbital? We
They
filled
will
the
be
bond molecular
uh,
orbital. What about the anti?
they will be left empty because we don't have any more electrons, right? They will
Oh,
have
okay,
no
okay.
electron. So if you have to calculate the bond order for this, then what you will do? Bond order formula is half number
Half a
of electrons.
number of bond and number of antibonds.
So how many electrons are in bonding molecular orbital?
Two,
What about anti? Zero.
zero,
So the bond order is what?
one.
So see, with the help of molecular orbital theory, we are able to answer why in H2 we only observe a single bond, right?
Oh,
Okay, so with the help of molecular orbital theory, we are able to tell with the experimental data that in between two hydrogens, we are going to observe a single bond. Okay, so let us talk about few more atoms so we have a better idea. Okay, so what we can do is let us uh, just exchange like take or give X electron to this hydrogen. Suppose we have this H2 molecule again, and what we did, we created a positive charge on it. By creating a positive charge, what we did actually, we removed the electron or not.
yes.
So now you have again two hydrogens, and out of these two hydrogens, one is bearing a positive charge. So you can
Okay.
either put the positive charge here or here. I am putting the positive charge here on the right side one. So this hydrogen is neutral.
So,
Hmm.
so it has no electrons.
This one will have no electron. So if you are doing the molecular orbital theory, now you only have one electron and you will be able to only place one electron here. So in bonding
Yeah.
molecular orbital, you will have only one electron, right? In H2 plus
Yep.
molecule, you will have only one electron in bonding molecular orbital. So what should be the bond order for this one?
Half
Half. Great. What about if you are giving an extra electron, H2 negative? Now,
in one
again,
of the hydrogen.
you will place a negative charge. Suppose I am placing the negative charge here. So instead of putting one electron, I am giving it two. So now
Then it will be three by no, it's minus row. It's half.
half again. But what is different here? For this one, we have a electron in anti-bonding
One
molecular
electron in
orbital.
anti-bonding.
So the bond order is again what? Half.
Half.
What else we can do? So if you compare the bond order, so the question was here, bond length order of H2 plus H2 and H2 negative. You have to tell the bond length order. So we know, see, if the bond order is one, if the bond order is one, that means we have a single bond, right?
Yeah.
And a single bond is going to be larger than a half bond. It is obvious. So the
Okay.
bond, okay, wait a second. So this is your bond order. Bond order is directly proportional to bond strength. We can say that. So bond
Yes.
order 1 is greater than 0.5. So the bond which is stronger is H21 because it has bond order 1. Then it is going to be H2 plus. Then it is going to be H2 negative. Can you tell me the reason? Although the value for bond order is 0.5, 0.5 for both of them. But why I have mentioned H2 plus as a stronger bond?
As the stronger bond than H2 minus.
Yes, although the bond order is same for both of them.
Um, because it's hmm,
Your favorite topic is going to be applied here.
none of these is my favorite. Um,
The one you
then
have frequently used.
huh?
The one name that you have frequently used so far.
Hmm.
It starts from
Okay.
there. Oh, Z, sorry, Z.
Oh, Zeph.
Yeah, think about it.
Because of Zeph.
Yeah, because of
Oh, okay, 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 okay.
right?
Because of, let me think. Because of high Zeph.
Yeah, if the Z is
Um,
high, it will pull the
so
electrons more close.
Zeph is related to this.
Hmm. Z is related to everything.
Okay.
Okay. So the opposite of you can say bond order, you can say like if the bond strength is higher, the bond length will be lower because this is your relationship. If the bond order is higher, then the opposite will be the order for bond length. So the question was about bond length. So this is your answer. You can relate it again with in terms of is if the electrons are more, then our nucleus will find it hard to like control all of them, and they will move far away from each other, leading to the bigger size, bigger bond length. Right?
Yeah.
This is just to give you a slight of like thought process, like how or in what ways they can ask you this. I have given you a way as well. For bond length, first check bond order. If bond order is same, then check number of electron or bond length. Negative charge, like negative Zeph wala scene, I have written it as well. Right. So let us talk about He2 molecule. Now, while we were discussing VBT, we came across the fact that He2 molecule cannot exist because the repulsive forces are more. And you told me something about like the He molecule, the orbitals are completely filled. So they won't be able to like take or like they won't be having a tendency to gain or lose an electron because they are stable. You told me something like this, right? You said like this is the reason why He2 molecule does not exist or not.
He2. Yeah.
So the same thing we are going to prove that He2 molecule does not exist with the help of molecular orbital theory. So let us start.
Because the
Again,
bond order is zero.
yeah,
What
again,
if
this
the
is
bond order is more than three?
if the bond order is more than three, you won't be coming across such molecules, but like we call this molecule like quadruple. See, those molecules look like this. You don't have to worry about them. You won't observe any molecule with a bond order more than three. Three is the maximum value for it. Okay,
Okay.
is this clear? Do I need to explain
Yeah.
it?
Nope. How much is the for this lesson?
This is the last part, right? This is the last topic, molecular orbital theory.
Okay.
I have written it as well. So non-existence bond, 4 electron, 8 electron, or 2 electron. Okay. Now let us talk about Li2. It is simple. You will be able to do it. What is different here is you have exhausted your 1s orbital. So if you have exhausted your 1s orbital, then automatically you have to go for the next one. The next is 2s, right?
Yeah.
So you will do the 2s. One thing
In a
for
different area?
with different, see, you merge 1s atomic orbitals and got molecular orbitals. This is complete.
Yeah.
Now you will take two 2s atomic orbitals and you will merge them and you will get atom molecular orbital from this 2s. Okay, then you will
Okay.
again put them away. Then you will reach to the next subshell or atomic orbitals. Okay,
P.
so till here it is very easy. Okay, but for P it is again easy, but people find it hard to like relate it. So I will try. You won't have any difficulties with that. So for now, is it clear?
Okay.
I was
Yeah.
saying something from your like from your exam point of view. You don't have to show this atomic orbital, molecular orbital. You have to, as we
Yeah.
talk about in valence for like valence electron, na, we always show valence electron. So in
Yeah.
molecular orbital theory, you can
Okay.
uh,
Okay. Okay.
adapt that way as well. You have to show only the valence molecular
Yeah. I
orbital.
understand.
So again, this is lithium 2. The bond order is 1, right? So this
Mm.
is what is HOMO and what is LUMO? HOMO is highest occupied molecular orbital and LUMO is lowest unoccupied molecular orbital. So they might ask you to identify which is highest, like HOMO, or which one is LUMO. So can you tell me, out of these molecular orbital, in which at molecular orbital the electrons are? The last molecular orbital with the electron, or you can say
The last,
the molecular orbital with electron with highest energy.
the highest energy.
Hmm.
Isn't it 2s?
Sigma 2s.
Uh, yeah, sigma 2s.
So you will call these molecular orbitals what? HOMO, highest occupied
Homo.
molecular orbital. Okay. If they give you a molecular orbital sets and they ask you to identify HOMO and LUMO. So for this one, HOMO is sigma 2s, right?
Yeah.
What about LUMO? LUMO is lowest unoccupied molecular orbital. Which atomic orbital has no electron?
Which
Molecular orbital.
atomic
Molecular
molecule
orbital.
has
Molecular orbital.
molecular orbital has more?
No electron.
No electron. In what element? In lithium?
Yeah, this whole thing.
No electron.
Hmm.
Um, no electron. Uh, there is no this like there's
You can just
no.
see this one. It is empty.
It's empty.
Yeah, it is empty. Like electrons are
Wait,
shown
just
with
one
it.
minute. You said lithium, right?
Ah, it is lithium. I am asking you the molecular orbital. Like if you see this one
Okay,
carefully, in this one we have no electron. Here we have two electrons, two electrons, two electrons. The molecular orbital with no electrons is a sigma 2s, sigma star 2s, right?
okay.
Are you, is it clear? Be honest.
No, like in how in lithium has like three electron. How does this make sense?
See, you have two lithiums, right? You are merging two atoms. One lithium
Oh,
has
okay,
three
okay, okay,
electrons.
okay.
The other one will have again three electrons. So now you have total six electrons that you are going to place in molecular orbital. In
Okay,
atomic state, they have three electrons, but in molecule combined state, now they possess six electrons.
okay. In that case, let me think.
Hmm. This is
Hmm.
see, this is your Li2. This is your molecule, and these are your atomic orbital. This is atomic orbital. This is atomic orbital, and but these are molecular orbitals.
Yeah. So yeah, you're right. The anti-sigma bond 2s is empty.
So we will call it what? LUMO, lowest unoccupied
Lumo.
molecular orbital. Is it clear?
Lumo. Can you spell that out?
Lowest unoccupied molecular orbital. Lowest unoccupied molecular orbital.
Okay. Lewis.
Lowest, minimum lowest.
I know the name Lewis, the person who created all this.
Okay, so the similar way we did for H2 negative, we can do this in terms of Li2 negative as well. Okay, the same concept is going to be applied.
Yeah.
So this is your question from your NCRT. Use molecular orbital theory to explain why Be2 molecule does not exist. You can simply use the help of bond order, and you can prove that bond order is zero. And if bond order is zero, there is no bond, so the molecule cannot exist. One more thing that I would like to add here is you have to show the atomic orbitals like this. This is your beryllium. This is your beryllium. They have their what? Atomic orbitals, right? Atomic orbital. How many electrons are present for your beryllium? The valence shell electron.
How many electrons there are in beryllium?
Yes, tell me that.
Four.
So, so let us write it down. We'll
Yes.
let us start with the
So
starting
to
one. One
make
electron.
Be2,
Hmm.
I will think. I will think. Uh,
See, see. Uh,
Isn't it like little close? You
We
need
don't have
some
space.
space.
See,
Uh,
let us try to like uh,
Make the four boxes in middle.
see. We will start with 1s or not? 1s, 1s.
Yeah, one
These
S,
are
one
atomic
S.
orbitals, right? In
That's
1s we have
two
two
S.
electrons. Two electrons like this. We can
Yeah.
fill. If we are
Yes.
merging two atomic orbitals, they are going to lead to
Two S.
molecular orbitals. Molecular orbitals, not 2s.
I know. Okay.
Sigma
Then
minus
sigma one S
sigma
two
star 1s.
okay, you're gonna put all datas. Okay, then
Sigma star 1s.
put two arrows in each box
Right?
because it's filled. Yeah.
Now our 1s
Now we
orbitals are
go
very
to
positive.
2s.
Hmm, good. Let us take it here.
2s has two electrons, so 2s2.
2s2 and
Mm-hmm.
2s2. Two electrons
Mm-hmm.
here, electrons here.
Mm-hmm.
Again, atomic orbitals are going to merge and give us molecular orbital.
Uh, yeah.
This one
Then
is
sigma
DMO,
2s2 and sigma 2s. Sigma 2s, sigma 2s.
sigma star
Um,
2s.
yeah, sigma star 2s for
Now,
anti.
if you have to calculate the bond order, then you are going to do what? You are simply going to
Count the bond
number of
molecular orbital number of bond molecular orbital minus the number of anti-bond molecular orbital.
number of
So
electrons.
1 2 3 4 4 minus 4 0, so bond order is 0.
That means this cannot exist.
Yeah.
Is it clear?
Yeah.
All right. So this is we have done this here as well. Now, I will do one thing. This needs some time if we have to introduce the p orbitals because you can see this look a bit weird, right? 2p,
Mm-hmm.
pi 2px and pi 2py. So
Mm-hmm.
we will do this in the next class because it needs time. And in the like 15 or 20 or like 30 minutes, we will do it in detail. You can ask me as much questions as possible, but you get this concept clear, right? And we will start the next chapter as well.
Okay.
So which chapter should we start?
um Thermodynamics.
Thermo?
Yeah, that's the next lesson, right?
Hmm. In your school, they have just finished the fourth chapter now. They haven't started anything new.
Yeah, they haven't started the thermo.
Okay, so your schools are going to like will open in August. No, in
Yep.
September or August. August.
uh, uh,
Your voice is not coming. Hello.
Say that again.
Your voice was not coming. Can you like plug in something?
Yeah, my headset disconnected. Yes. Last of order, August.
Okay, so we have the whole August and we have like July as well. So we
Yeah.
will be able to complete thermo plus ionic or like equilibrium chapter as well. Once we have
Yeah.
completed the equilibrium, then we will have like the redox chapter. It might take two classes, like at most. Then we have what organic, and your
Yep.
syllabus will be complete. We can complete it, and we will do something. All
Mhm.
right. So till now, if you have any doubts or questions, please ask. Get this concept clear because they are going to ask
No,
you.
no doubts, no doubts.
Sure.
Yeah.
Okay.
If
So
I had doubts, I will just go through again, go through the whole PDF. If I still have doubts, I'll ask you.
mm, collect your doubts and ask me like get this chapter clear. Don't
Yeah.
like left any doubts. Try to collect as much as possible and ask me the next. Okay.
I'll be starting revising every